Hello, good people. Welcome to the first videos of Unit 8. Unit 8 is going to take us into the application of definite integrals. So all the work that we did in Unit 6 to try to evaluate definite integrals, here we're going to get some uses for why we do that. In the first two units that we're going to cover here in this series, they're familiar topics. So I wanted to formally define the average value of a function, even though we have alluded to it earlier in the semester. So we're going to start with a quick review. And the quick review has to do with a theorem, and it's called the intermediate value theorem, or the IVT. IVT, the intermediate value theorem. What the intermediate value theorem says is if I have a continuous function, and here's my generic function, right? F is continuous. So if I know that my generic function f is continuous, if I choose an x value starting point and I call it a, and I choose an ending x value and I call it b, and I'm talking about this interval between a and b. A has an output or a y coordinate of f of a, and b has a y coordinate, an output called f of b. So what the intermediate value theorem says, if I choose a value that's between those values. So I'm going to say that one's called L. So if I choose L, which is somewhere in between here, I don't know, somewhere here, doesn't matter where you put it, as long as it's in between. Here's what the intermediate value theorem guarantees. If my function is continuous, it guarantees the existence, there exists an x value, which I'm going to call C, on the interval from A to B, such that such that f of c equals that y value. So if the function is continuous and I choose any interval from a to b, and I look at the y coordinates of a and the y coordinates of b, I can choose any value here, and I can guarantee you that somewhere in that little window the graph exists, and I can call this c for any point in between f of a and f of b, or for any value for between f of a and f of b, right? So intermediate value theorem really has to do with the consequence of continuity. The other big idea that I want you to remember is the average rate of change. Now, the average rate of change says if you want to figure out how fast a quantity is changing, then subtract the outputs on a given interval and divide by the length of the interval, which is b minus a. And that's related to the mean value theorem, which says if you take the derivative, which is the instantaneous rate of change, at any given point, or there exists a point in my window, if my function is continuous and differentiable on an interval, where there is a point at which the instantaneous rate of change equals the average rate of change. So the mean value theorem, like the intermediate value theorem, those are existence theorems. They tell us that something exists. There exists an x equals c value on that interval that we started with, such that f of c is that random, I shouldn't say random, but that value that I picked in between f of a and f of b. The mean value theorem says there exists, if my function if f is continuous and differentiable, on the on the interval between a and b, I know that there exists an x value where if I take the derivative at that x value, it equals the average rate of change of the whole interval. And then this just tells me the average rate of change of a given interval. Okay, so here's what we're doing. We're going to use some of these ideas to figure out what's going on here. What we're going to be looking for is the average value of a function. And the average value of a function, given the function f of x, and I'm going to name it. You can call it whatever you want, but I'm going to call it the function f of x. We can find the average value of a function on a closed interval by saying it's 1 over b minus a times the integral from a to b of that function. For those of you with a good memory, when we were talking about interpreting definite integrals, we saw this in the front. We saw a fraction in the front, and that had to do with this average value idea. So, for example, in number one, if I'm talking about the interval between -1, which would be from this point, to 3, which would be this point. So, in this window, right, in this window from -1 to 3, if I were to look at all of these y coordinates, all of these function values, what would be the average out of all of these y coordinates? Some of the y coordinates, some of the function values are positive, some of them are negative. If I were to take the average of all of these, what would that be? So this equation or this formula says you can find that by doing this idea. And if you think about it, the reason it works is, remember, a definite integral, this part, is adding an infinite number of things. Specifically, it's adding an infinite number of rectangles that are really, really thin. So we're basically adding all of these y coordinates because the y coordinates are the heights of those rectangles. So we're adding all of them in between these, and I guess I should do these as well, right? I'm adding all of these, and then I'm going to divide by the interval where we're looking. So when I find the average value of f of x, the average value is, according to my formula, 1 over b minus a times the integral from a to b of my function 6 minus x squared dx. This is how I'm going to figure this out. Now, here's a setup. If I'm doing a free response question, this would give me some points, a point, 2 points, I don't know. Not a lot, but at least I'm showing people that I know what the formula is. But now let's figure it out. So 1 over 3 minus -1, that's 1/4, times the integral from -1 to 3. Well, why don't we just take the antiderivative? Because I can take the antiderivative of this, and then I can evaluate it at 3 and -1. So the antiderivative would be 6x minus the antiderivative would be x cubed over 3, and we're going to evaluate that from -1 to 3. Cool. Doing that means I'm plugging in a 3, right? So 1/4 times 6 times 3, that's 18, minus 27 thirds. So all of this is what happens when I substitute the 3. But now I have to substitute the -1 and subtract that. So I have to be careful with the minus in the second part. So -1, when I substitute it, that's going to give me -6. When I substitute it over here, that's going to give me plus 1/3. Do you see that? Do you see that? I substitute this in here, that'll give me -1 to the third, that's -1. But there was a subtraction going on, which is why I changed to that. Cool. I'm still going. So this equals 1/4. I believe this is 9. So 18 minus 9 is 9. Plus 6, that's 15, minus 1/3. So I believe this is what I have. And I guess I can change this. This is 14 and 2/3. That'll be 45. Oh, shoot. Where did I go? Where did I go? 14 and 2/3. That's what I needed. And then I'm going to take 1/4 of that, right? 14 and 2/3. I believe that's 44 thirds. 44 thirds. And when I multiply this, I'll get 44 twelfths. And I believe I can divide by 4, and I'll get 11 thirds. This is the average value. 11 thirds is the average value, or 3 and 2/3. So if I were to add all of these y values, now notice I have to count this y value once, but then I got to count this y value again. So it's going to be kind of loaded with repeating heights over here. But if I add all of these y values, these function values, even the negatives, the average of all of those is 3 and 2/3 or 11 thirds. That's the average value. Now the question is, okay, well, 11 and 2/3, which is 3 and 2/3, is somewhere here. The question is, where does this occur? And that's the second question that's given here. When does the function actually assume this value? When does it produce this value? So to figure that out, we know the y value, we have the equation, so let's solve for x. So I'm going to add, actually, I think I'm going to add the x squared this side and subtract the 11 thirds to the other side. So it'll look like this. And I can fix this. I believe this is 18, this is 7 thirds. And then I can take the square root. So x equals the square root of 7 thirds. And whatever the square root of 7 thirds is probably somewhere in between 1 and 2. And when I say probably, it is somewhere between 1 and 2. And that's when it's going to reach that average height. Okay, so we did a little bit more than we needed to, but I need you to understand that this formula is going to help us find the average value of the function if we're given the function, right? We have to be given the function that we want the average value to. We can use this formula to figure it out. All this other stuff was just taking the definite integral, which is what we did in Unit 6. But the formula is what got us what we needed. We'll come back in the next part and we'll talk about some more applications.